The mechanism of linear spatial filtering using a 3 by 3 neighborhood is illustrated over here. At any point xy in the image, or for every pixel p having coordinates x, y in the original image, the output or the response g x, y of the filter is the sum of products of the filter coefficients and the image pixels encompassed by the filter. As I told you earlier, that a spatial filter is also known as a spatial mask or a filter mask. You can observe here that the center coefficient of the filter W 0, 0 aligns with the pixel at location x, y. In the example shown over here, the size of the filter is 3 by 3 and the response g x, y is a sum of 9 terms. Each term is a product of the filter coefficient and the image pixel at that location. For example, the first term of this summation is the filter coefficient W minus 1, minus 1 multiplied with the intensity at the location x minus 1, y minus 1. The second term in this summation is the filter coefficient W minus 1, 0 multiplied with the pixel intensity at location x minus 1, y. Likewise, there are 9 terms or 9 products which are summed together in this particular example. Further, we see that for a mask of size m by n, m is equal to 2a plus 1 and n is equal to 2b plus 1, where a and b are positive integers. This also tells us that we work with odd size filters, and the smallest size that we consider is of a filter of size 3 by 3. Because if a equals 1 and b equals 1, in that case m is equal to 3 and n is equal to 3. Henceforth, the smallest size of a filter in our case is 3 by 3. Now, there are two common linear operators which help in computing the sum of products of the filter coefficients and the image pixels, and these are correlation and convolution. Correlation is the process of moving a filter mask over the image and computing the sum of products at each location. The best way of understanding the process of correlation is through an example. Therefore, we begin with a one-dimensional illustration. The figure on the right shows a one-dimensional function f and a filter w. Part B shows the starting position for performing correlation. The first thing we note is that there are parts of the function that do not overlap. The solution to this problem is to pad or attach function f with enough zeros on either side to allow each pixel in the filter w to visit every pixel in the function f. Now, if the filter is of size m, we need m minus 1 zeros on either side of function f. Part C over here shows a properly padded function. The first value of correlation is the sum of products of function f and w for the initial position shown in part C. As you can observe that when 0 is multiplied with 1 and added with 0 multiplied with 2 and added to 0 multiplied with 3 and then added to 0 multiplied with 2 and then added to 0 multiplied with 8, the answer you can observe in part G is also 0. Then we in order to obtain the second value of correlation, we shift W 1 pixel location to the right and compute the sum of products. The result again is 0. In fact, the first non-zero result is when the filter W has been moved 3 positions, in which case the 8 in W overlaps the 1 in F and the result of correlation is 8. Proceeding in this manner, we obtain the full correlation result given in part G. We then crop the result given in part G so that the output is the same size as the original function f. The final result after cropping is presented in part H. Two important things are to be noticed over here. Firstly, correlation is a function of displacement, or let's say the movement of the filter. As you can notice, the first value of correlation corresponds to 0 displacement of the filter. The second value of correlation corresponds to 1 unit displacement, and so on. The second noteworthy thing is that correlating a filter W with a function that contains all zeros and a single one gives an output which is a copy of W but rotated by 180 degrees. We call a function that contains a single one with the rest being 0 a discrete unit impulse. So we can rightfully conclude here that correlation of a function with a discrete unit impulse gives a rotated version of the function at the location of the impulse. The preceding discussion on the correlation of one-dimensional function f and one-dimensional filter W can easily be extended to images which are two-dimensional functions. For a filter of size m by n, we pad the image with a minimum of m-1 rows of zeros at the top and bottom and n-1 columns of zeros on the left and right. In this case, m and n are equal to 3, so we pad f with 2 rows of zeros above and below and 2 columns of zeros to the left and right, as is shown here in part B. Part C shows the initial position of the filter mask for performing correlation, and part D presents the full correlation result. Part E shows the corresponding cropped result. You can again note over here that the result is rotated by 180 degrees. Further, the general formula for correlation in images is also presented. We now move to the second linear operator, convolution. The figure on the left, which is the correlation of one-dimensional function f with one-dimensional filter W, is the same as the one given on the previous slides. It is only repeated here for convenience and for facilitating a comparison between correlation and convolution. As before, in order to understand convolution better, we can look at an example of a one-dimensional function which is convoluted with one-dimensional filter W. It is noteworthy that the mechanism of convolution is the same as correlation, except that the filter W is first rotated by 180 degrees. This can easily be observed in part I of the given figure. The filter W is first rotated by 180 degrees. The rest of the mechanism is the same as has earlier been explained for correlation. The function f is padded with the necessary amount of zeros. The sum of products is obtained. The full convolution result is presented in part O, and the cropped convolution result is presented in part P. It is noteworthy that the result of the convolution is the same as the filter mask W. It is noteworthy that when the filter mask W is convolved with a discrete unit impulse, in the output we obtain the filter mask W as it is. Same as before, the concept of convolution is now extended to images. It can again be noted that the filter W is rotated by 180 degrees, and the rest of the procedure is the same as was followed in correlation. The filter W is slided across the image fx, y. The sum of products is obtained, and the full convolution result is presented in figure G. Further, the cropped convolution result is presented in figure H. The general equation for implementing or performing convolution is also given here in this slide. Lastly, it is again noteworthy that convolving a filter W with a discrete unit impulse gives on the output the filter W as it is. Now, using correlation or convolution for performing spatial filtering is purely a matter of preference. Spatial filters can be divided into two main categories: smoothing filters, which are equivalent to low pass filters, and sharpening filters, which are synonymous with high pass filters. Both smoothing filters as well as sharpening filters can be linear as well as non-linear. If I look at smoothing filter in further detail, averaging and Gaussian smoothing filters are examples of linear smoothing filters, whereas median, min, and maximum smoothing filters are examples of non-linear smoothing filters. If I look at sharpening filters, Laplacian, high boost, and unsharp masking are example of linear sharpening filters, whereas gradient is an example of non-linear sharpening filters. We will, in the next lecture, look at the smoothing filters in more depth.